Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today is going to take a look at binary shifting and binary rotation instructions and their applications as it applies mostly to the x86 assembly language, but the basic high-level stuff obviously applies to everything you can think of in computer science. So a logical shift, you're going to see a difference between a logical shift and an arithmetic shift here. And so when we shift digits one way or another, either whichever way we do this, we're shifting to the left or to the right. And we're filling a hole, and then what are we going to fill that hole with? A logical shift will fill in with zeros, especially in this case, if I'm going to the right. So this basically means that logical shifts deal with unsigned integer shiftings. And you're like, well, what? And again, you're like, what is the application of this? And again, this is pretty cool stuff, because when I think back to my 4th grade arithmetic lessons, when I do this kind of stuff, and I say, if I had like the number or the 900, and I say divide that by 10. And you just take the 900 and you basically just chop off the last digit and you're like, I got 90. And it's the same deal here in binary, where you're just taking this number, whatever number this is. I guess this is 207. Let's just go with that. I'll just trust it. And if I shift everything over and I put a 0 in the spot, basically the most significant bit, and remove the remainder, the carry flag will hold the remainder of this, you'll see that you end up with, this is where integer division comes from. 207 divided by 2 is 103. And the remainder is just lost. And that's the difference, the huge difference between integer division and floating point division. So again, the least significant bit is technically lost in the process, but it's moved into the carry flag in case you want to find the remainder of this. So you can think of it like the remainder of a division by 2. And so yes, we use different ways of determining even oddness of numbers, and this is one way you could go ahead and do that, is just to take a number, rotate it right, and check the carry flag. Or you can AND it with 1, or test it with 1, or you can mod it by 2. There's so many different ways that you can determine even or oddness when it comes to numbers. So arithmetic shifts, they do the same stuff, but now there's a question. So there's always a question to be asked when we're dealing with signed arithmetic. So we're still shifting to the left or to the right as need be. We're filling the hole with something, but then we don't know what we're going to fill it with, because it all matters if the number we're going to be shifting is a positive or negative number, because the whole point of shifting everything back and forth is to make sure we keep the number exactly the same, divided or multiplied by 2. And in this case, if I just replace this, if I replace this with a 0, well, this 0 here instead of a 1 would indicate that my number is a positive number instead of a negative. This number needs, as a negative 49, if I do this operation, I need to reduce down to negative 24, negative 25, and this is where division math gets funny on us, because negative 49 divided by 2 is actually negative 25, remainder of 1, because just check it out and you can do the math yourself if you're interested. So the same things go. The carry flag holds basically the remainder of the division, and the most significant bit, this is the big one. If it's a 1, you can see it, it goes into 2 places. It sticks around and it shifts over, but everything else just shifts over 1, and then the least significant bit moves over into the carry flag. So that's how we handle both of the different kinds of shifts. Now let's take a look at how we can apply them in actual x86 assembly language instructions. Okay, so to shift left, basically both logical and arithmetic shifts are the same, and that's because I'm essentially multiplying by 2. Just like if I took the number 90 from a couple minutes ago and I said, let's multiply that by 10, we get 900. You don't add a 1, you don't add a 2, you add a 0, because you're multiplying that whole thing by 10 and shifting over, basically shifting the decimal point 1 space to the right. And the same thing goes here, where it only makes sense to add a 0, so it doesn't much make sense if it's arithmetic or logical. It's going to do the same thing. It's going to add a 0 to the least significant bit over here and then shift everything over. And again, the carry flag will always get that 8th bit one way or the other. So it will hold this, and you can basically determine if you overflowed or underflowed or whatever it is that you're trying to do. So, and again, coming back to this, the computer, the CPU has no idea what it's doing. It's just given these, these bits in this specific format. It's told to shift to the left, and it just does what it needs to do. So this operation here, they're both identical. And let's see, that is because adding anything other than 0 makes no sense, as I was describing. So it doesn't much matter here. So if 207 is shifted to the left, you get 158 because there was an overflow. Or if you get negative 49 and you shifted that over 1 to the left, because it all matters what you're doing, right? So negative, that comes out to actually negative 98 because 207 times 2 overflows, but negative 49 times 2 does not. So that shows off. And there's many different ways you could go ahead and do this. Notice though, you pretty much have to set up an immediate hard-coded literal value for the amount of shifting you need to do, or you need to very specifically use the CL register for this. Why the CL register? Who the heck knows? That's just what the engineers and the architects of these computer systems designed for us, so we have to follow suit. So again, what is the real purpose of all of this? The real purpose of this is to have the fastest type of multiplication that you can do on a computer in the modern world, because of the way binary works, because multiplication and division are general use operations. And so you're used to, what's 19 times 72 or something like that? Well, there's a huge algorithm that goes into that. Think of fourth grade arithmetic again. All you have to do, do all the multiplications, do all the additions to try to figure out what the end result is. But and we're discussing, if I multiply by 10, then it makes it a lot easier because I just slap a 0 on it and I just say done. But it's not the same here. Well, it is the same here, but in powers of 2 when we're talking about binary. So every time we shift 1 to the left, we're multiplying by 2, and every time we shift to the right, we're dividing by 2. So continually shifting means to continually to be, basically multiplying by another power of 2. So in this case here, if I take 5 in here, 1, 0, 1 in binary, and I shift everything over to, 1 space to the left, and put a 0 in there, you can get, this is 1 plus 4, and this is 2 plus 8. And so if you wanted to even move one more over, this would be 4 plus 16, that would be 20. So you can see, and then even do that again, you'd get 40 in binary. So by shifting 5 over 3 times, come back to here, 1, 2, 4, 8 plus 32 gets me 40. So obviously it works, otherwise it wouldn't be talking to you about it, and our computers wouldn't be doing all this work for us. So it's the equivalent of doing 5 times 2 times 2 times 2 to get me the 40. And so 3 shifts over gets me there. 1 shift over gets me power of 2, multiply by 2. So again, shift right, this is the logical shift. So shift, this is just SH right. I don't know why, it should maybe SL, I don't know. They designed the terminology. So shift right, logical shift right instruction. So this is the unsigned mathematical operation to divide by 2. And so this means that no matter what I'm doing, I'm dividing by 2 and adding a 0 to the most significant bit as we go. Because it's unsigned, this 1 doesn't possibly mean anything negative, it just means that it's 128 something, right? 128 plus whatever other digits have been set to 1. So shifting, so we're dividing by 2 again, and the same as before a minute ago, every time I shift over 1 time, I'm dividing by 2. So if I take 10, come back to what we were discussing here, and I take 10 in binary, shift it over 1 time, that kicks me off, basically brings me over the 0, the remainder gets stored in the carry flag, and we're left with 1 plus 4, or 5. And the same with 40. If I take 40 and I shift over 3 times, I go kick off this, move everything over, add zeros to the left-hand side, 1 plus 4 is 5. 40 divided by 8 is 5. So that works perfectly well. And so again, the arithmetic shift is very similar, but again, it just comes down to see how this is different. Instead of just this being a blind 0, whatever bit is here in the most significant bit, that sticks around and also gets shifted over, and everything else gets shifted, and the same thing goes for the carry flag. So dividing by 2, but we're doing it to keep the sign of the value equivalent, because if I took negative 40 and I divided by 2 and I got positive something, obviously the math wouldn't work out right, and that's not why we're doing this math the way we're doing it. So coming back here, so again, if this is a positive number, there's no difference. 10 divided by 2 is going to be 5, whether it's a signed number or unsigned number, positive. And so 10 shift over to the right, because this is a 0, the 0 stays in here, and I get 1 plus 4 is 5, as I did in the previous slide. But now this is where everything gets a little funky, right? Because now this is negative 40 in pure binary. That's, with the most significant bit as a 1. So this is 2's complement math. And so if I divide this by 8, or I shift this over 3 times, This now, because it's SAR, I'm adding the ones along the way instead of zeros. And now, if you can do the math right, this is 4 plus 1, this is -5, this is -40 divided by 8, and that gets the answer, of course, that we're looking for in this case. Okay, so let's go ahead and look at some problems to do. So I've already went ahead and converted our hex digits here into binary, so 8C, 9D, and now we just have to follow the instructions that they have for us here. So shift this guy right 4 times over. So basically these 4 go away, right? Because if they're cut down, just remove 4 and shift everything over. So 1000 remains, and because this is a shift right, so this is a logical shift right, I'm filling in those spaces with zeros. And so that's what would happen if I take this and shift right. And now if I'm going to go back to the left, then it always fills in with 0. So I'm just going to basically just take these 3 zeros off and replace it, so I get 0, 1, 0, 0, and then I'm replacing everything with zeros. So that's what we should get out of this. So what number is this? Let's see, we'll come back and do the other one here in a second. And we can see here that this is 128 plus 12, so this is 140. And if I'm taking this and I'm dividing that by 16, I get 8 out of the deal. That's what, 2, 4, 8, 16. That's what I'm dividing out of. So I get 8. There would be a remainder, but we're not worried about that because that's not what we're doing here. This is integer division, basically. And then if I take 8 and I shift left 3, that's multiplying by 2, 4, 8. I better get 64 out of the deal, and I do, because that's the 64's bit right there. So that's working for me. So again, arithmetic versus logical shifts, it's the only thing that makes this challenging. So let's see, SAR shifting to the right. So this value here, this is a negative value because I'm dealing with signed arithmetic. So what would I do here? I'm basically cut off these first 3 digits, move everything over, so I should get 1100, or say 0011 if you're going in reverse. You say, because what am I doing again? I'm cutting off these 3 digits and then moving everything over, so 1100, and then there's a 1, and then there'll be 111. So this should be, if I did this right, it should be 1111. And let's see, is it 11110011? Because this is -99, just going off what they showed us. Let me put this back how it was a second ago. This is -99, and I'm dividing by 8, so I'm getting -13. And again, it's a little weird because you're like, well, maybe it's -12 or something like that, but the way the math works out, the division goes on the high end when it comes to negative values. So then coming back here now, SAL versus SHL, exactly the same stuff. So if I'm going to take this value and shift over 2 to the left, I'm going to add zeros. So I'm going to get 1100, and then cut off these 2, and I get 1100 on this end too. And you could, so 1100, 1100 comes out as a -52 because that is moving over 2 times, shifting twice, multiplying by 4, my -13 turns into a -52. So that pretty much covers arithmetic shifting. We'll cover this again in a couple slides up when we do applications of this, but let's cover some of the lesser known and lesser important other shifting and rotating operations, and this is one of them, rotate left. So each bit gets shifted to the left. In this case, look at the little graphic. So in this case, the carry flag holds the most significant bit, and it also gets shifted around. So when you're doing a bit shifting, you lose bits in the process, right? You're changing the actual number, if you want to think of it. And you are changing the number here when I'm rotating it, but in this case, you're keeping the bits, you're just kind of shifting it around. If you had like a bracelet or something, like everything is still in the correct relational order. It's just that they're shifted around, they're rotated around on your hand or on your wrist. So pretty much that all goes. And so what's cool about this then is if you took this and you shifted over one by one, you could use the carry flag to determine what each individual bit was. And in this case, if I kept rotating one time, and I did it 8 times over, I would be able to analyze every one of the 8 bits, and then my number would be put back to what it was when it started. So I wouldn't lose the original value at all whatsoever. So that's pretty cool. I like how that works out. So the examples here, F0 hex, so 1111 0000, rotate left 1, just bring that 1 over and shift everything over, and there you go. 3F 0011 1111, take it and rotate left 4. So that rotating 4 in this case means basically just to take the nibbles and switch the nibbles up, because you can see it's 1 1 1 1 over here and 0 0 1 1 over here now. You've just taken each of the 4 bits that are individually part and then just swapped them. And so ROR is the exact same thing, just in reverse, of course, because the least significant bit gets moved to carry and gets brought around to the most significant bit, but everything else gets shifted one place. So same rules, F0, 1 1 1 1 0 0 0 0, move over 1, and now you can see 0 1 1 1 1 0 0 0. And the same thing goes 3F, and again you can see ROR and ROL, when I'm doing 4 at a time, I get the same results. Because again, no matter if I'm shifting left or right 4 for an 8-bit quantity, I'm just taking those 2 nibbles and I'm switching them up. So that's all there is to it there. So let's take a quick example look at this. So we have 6B in hex, 6B. We have 9D in hex, and we're just going to follow these operations. I'm going to take this and rotate everything 1 to the right. So what am I doing? I'm just basically taking this, the least significant bit, and I'm going to the right and getting it and bringing it back over. And then I'm taking this bit and moving it over into this nibble. So that should do that. So that brings everything right 1. And then if I'm going to shift everything left, what am I doing here? So this 1 0 1 comes back around. So this should be 1 1 0 1 if I did it right, because I'm taking the final one over there, and then this should be 1 0 1 0 if I do this right. And let's see, did I do this problem right? 1 0 1 1 0 1 0 1 1 0 1 0 1 1 0 1. So yep, that's looking pretty good. So let's see for the second one doing the same kind of stuff. So if I got 9D and I'm ROLing it 4 times, and again, coming back to what we just discussed, it wouldn't matter if I'm ROLing or RORing. All I'm doing is shifting the 2 nibbles. Oops, that's not 2. And so to do that right, so just, these 2 swap out, and so everything's looking good. And then if I rotate this 2 times over, the 0 and the 1 come around. So this should be 0 1 1 1, and then this should be 0 1 1 0 if I did this right. So let's see, did I do this? So there's, switch the nibbles up, 1 1 0 1 1 0 0 1, and then 0 1 1 1 0 1 1 0. So good, I did everything like I was supposed to. Only took 16 takes. No, only took a few takes actually, because I got the math wrong the first time. And that will happen. You will get the math wrong occasionally, because this is really tedious and really boring stuff, and that's why we have computers to do all this for us. It never complains yet, right? So moving on here, do not worry yourself with these operations. I just wanted to show you that they exist and the book covers them. So RCL, rotate, carry left. I do not know why you would need to do these things, so if you have an answer for why these operations exist, please let me know. The application does show it, but like in a modern context, I really don't 100% understand what's happening. So you rotate plus you carry. So in essence, the carry flag becomes an extra bit, if you want to think of it this way, because the carry flag moves on over into the least significant bit. The most significant bit moves over to the carry flag. So you essentially get 9 bits out of the deal. So I'm like, okay, if you want to follow along, I'm not gonna, me personally, never gonna test you on these things, but just so you know it exists. And the same goes for RCR. You get an extra bit, but the carry flag is basically right, functionally speaking, right of the least significant bit. And so the least significant bit moves over, the carry flag moves back to the most significant bit, and so forth and so on. And so if those don't matter, these definitely don't matter. Whew. Shift left, extended shift left instruction, extended shift right instruction. And so you can take a destination and a source sequence, and you can take bits from one register and move them on over without affecting that register, and you can rotate. I do not have a clue what you would do this for. And so you can see here, if this is my AL destination, this is my BL source, by trying to shift everything 1 over, this stays the same, but this bit moves over, and then everything in the destination goes over like it's a normal rotation. I'm sorry, like a normal bit shifting, like an arithmetic or logical shift to the left. And the same goes, but in complete mirror image reverse for shifting to the right. So here's my source that does not get modified, and my destination does. So the least significant bit moves over, everything else comes along for the ride, and then the 1 gets put into the carry flag. Like that's as much as I'm going to talk about it. So we're ready to move on. Looks like we're ready to talk about applications of all of these operations. or in this case, we're going to mostly focus on the bit shifting because that's the most relevant to everything we're doing in this class. So now let's take a look at our first application, and this one isn't readily relevant to our lives, but it definitely is a good thought experiment. So what if I had a custom large integer? So we normally deal with 32 bits or 64 bits, but what if we had a 12-byte integer someday in the future, or in some kind of Python-y system, or who knows what? How might we shift all the bits of this 12-byte number over 1 bit? And so this is the code that makes it work. And again, there's really no reason to go crazy into it, but Python does do this automatically, thank goodness, right? But we would have to write all this code ourselves. So we're like, okay, I have an array of bytes because there's really no way to do this other than just to do this, 1 byte at a time or 4 bytes at a time. 4 bytes is if we can get away with it, which we can. And so in this case, okay, why? I don't know why we have ESI to 0, and we're just, oh yeah, I guess we could just hard code this, but we can say, okay, shift right everything in ESI plus 8, move it over 1, and then rotate with carry to the right. Oh boy, we found an actual reason to use this thing. And then rotate with carry one more time over, and you're like, well, why are we doing this? Why are we doing this the way you see this and not the way you think? And it comes back to endianness order here. Because the first couple times I went through this, I'm like, oh, this isn't doing what it's supposed to do. There's a 0 where it doesn't belong, and you can see that on that useful red circle there, or what is going on in there. There's a 0 there, and that's because this is the most significant, or the whatever, but according to the endianness, right? Because everything goes in byte order, shifted, or basically reversed. So this is actually doing things correctly. It takes all the values, because 9 is 1001, right? I have to kind of look at myself here, so let's see if I can zoom in a little bit here. Let's see if we can see it a little easier. And so, is it getting any better here? Let's see. So everything is basically 1001 all the way across, right? Because it's just 9s across the entire board, and so that becomes 1100 for everything but this guy right here, and that's because the little endianness, the last double word is where that hole needs to be filled. And so 4 bytes of storage, it gets weird when you do this kind of stuff, because especially little endian versus big endian, how do you know what endianness you're dealing with, and this and that? So this only works with little endian order. I just wanted to show it because the book shows it, and just to go, aha, maybe it clicks for you, and most likely it doesn't, which is fine. So, but there is a good example of using rotate with carry. So application number 2, something that's a little more near and dear to all of our hearts, fast binary multiplication. So what you see here, 123 times 36, if this wasn't binary, this would look exactly like we would in 4th grade arithmetic again, because 123 times 36, you do the math, you would tally up all the numbers, you shift things over. You're essentially doing the exact same thing, just with a different base system. And so this is 123 in binary, this is 36 in binary, and so what's going on here is 36 is 2 shifted over, which is 4, right? 2 to the 4th, 2 to the 2nd power is 4. So this is 4 times a number, and this is 32 times a number. So what does that mean? So using which I can never remember which property of mathematics it is. 36 can be broken into 32 plus 4. So if you can take 123 times 32, you can add that quantity plus 123 times 4. So there you go, and you get 4428 out of the deal. And so how do you do this in a general case? That's a homework assignment or an in-class assignment. I give you the pseudocode or the C++ code that actually does the work. It's your job to convert that into assembly language. But here's something like that. This is just going back to this again. So 32 plus 4 times 123, just using, let's see, does it say which? The distributive property, there we go. So using the distributive property of mathematics, then things break down this way, and we can break this down into a simpler way to do this. Why, again, do we care about this? If we care about performance, and we care about the speed, this is one addition, or 1 addition, 2 multiplications, or 1 multiplication versus, what is this here? 2 bit shifts and an addition. The 2 bit shifts and addition is always going to win out to the multiplication. And so for when you're doing a lot of math and you need to do it quickly, like video games, you're gonna find ways to do things this way to reduce the math down and make it work as efficiently as possible, because all those clock cycles are just getting wasted. Like most other applications, a bank app maybe doesn't, you don't have to worry about that kind of stuff. But if I'm trying to push pixels out as absolutely fast as I can, this is definitely one way to go about doing this. And so for that other example, back to Human Resource Machine, that game that you hopefully played for homework assignment, or you've played somewhere, or you've seen it somewhere in your life, there's a level where you take any value and you multiply it by 40. And it's the same rule here. The distributive rule applies, and I can turn 40 into its powers of 2, 32 plus 8, and so now I can take 8x plus 32x. So that's how the level gets 1. And so just to come back, just to finish this up, how would I write this in assembly language? So there's many ways to do this. I don't know exactly how many ways to go about it, but if I wanted to multiply 123 by 36, well, I would put 123 into EAX. Then I would basically shift everything over, move that into EBX, because I need to do 2 separate multiplications that get summed together. I take one of them, I shift over 5, because that's my 32. I do the other, I shift over 2, so that's multiplying by 4. I add the 2 together, and so let's say this is a kind of maybe a little misnomer. When you get to this line of code, the final add, EAX does hold 32 times 123, and EBX holds 4 times 123. You add the 2 together, and you get the final result of 4,428. And so, is this right? 319 times 18? Does that get you to the same number? And I'm not 100% sure about that. I am interested. I have to trust my own PowerPoints. Oh, that's not right. Oh boy, 5,742. And so, to go about doing this, you say, oh, put 319 into EAX, and the same thing goes. I'm going to take the easier number. 18 is easier if I break it down into 16 and 2. So in this case, I have to take the number, put it into 2 separate registers, shift over 16, so that's 4 times 2, 4, 8, 16. So I shift that over to get me to 16 times, and then I shift the other one over 1 to get me to 2x. So then I add the 2 together. 16x plus 2x gets me 18x. So I'll have to fix this PowerPoint up, but otherwise everything's looking good here. And so you can do this across the board. If I needed to, add 3 of them together, I could set up 3 registers, do whatever I need to do, and keep on going. So other than the fact that you're fighting for register space, there's really nothing overly challenging about it. Break the problem down using the distributive rule and go to town. Okay, so speak of the devil, here is an our turn, your turn, where we're going to take whatever is stored in the EAX register, and I'm going to multiply it by 26. So I'm just going to pop a 19 in because this is my second time doing this. And so we're going to use EDX. We're going to follow a slightly different algorithm here, so we're not using 3 separate registers, because 26, remember, of course, is 16 plus 8 plus 2. So there's 3 different terms we would have to factor in. So if I shifted this one over 4, I get the result. If I shift this over 3, I get the result. And I shift this over 1, I get the result as well. So it's just a matter of basically adding to the complexity of this all. So let's kind of go through this. So I've already put the 19 into the EAX register, and I'm going to copy it over into EDX. And then I'm going to shift left this thing 4 times. And this is the same as multiplying by 16. So the EDX register right now holds 304, which gets pushed onto the stack. Completely different way of doing things this time. And so now I take the 19 and I copy it back again. So now the 19 is stored back in EDX, and now I'm going to shift that over 3 times. And that's the same as multiplying this by 8. And so I get 152 in here, and then I immediately take this guy and I shift it over 1 time to multiply it by 2. And so now I have the 3 quantities that I have to sum together. And so now you can see the result of this. Take whatever's in EDX and add it on in. So I'm just going to take this, so whatever, plus 152. And so 190 is held in the EAX register. And then I'm going to pop off the 304 and put it into the EDX register. And then I'm going to add it in 1 more time. Plus 304. And you get 494. The stack is empty. EDX holds 304. EAX holds 494. Let's make sure that that is correct. Whew, we did it right. So there we go. And so, again, this is only one of many possible ways, because you could do like we did before. You can use 3 registers. It's just wasteful. especially if you're fighting for that register space already, because if you're using EAX and EDX for multiplication or division, you're using ECX for looping, you're using ESI or EDI for pointers, goodness gracious, right? It can get challenging, and that's why this is a pretty good methodology to use pushes and pops, use the call time stack to handle this kind of stuff. So pretty good example here. Let's move on. Here's an application that is much more near and dear to my heart. Video game stuff here. So back in the old days, back before graphics cards and all sorts of crazy stuff, you could directly access the physical hardware, crazy amount more than you can now. And so you could actually physically go in and you could actually touch the buffer that stores, all the video information. And so for good old mode 13H, mode 19 graphics, you would have a whopping resolution of 320 by 200 pixels. And you're like, okay, that sounds amazing, right? It was cool for the time, of course. Doesn't hold up 100% like it did back then, as you can see in this picture. That was amazingly colorful graphics for back then. But what was cool about the different for its time is that you could actually have one of 256 different colors for each of the pixels, meaning that each pixel was 1 byte in memory, because basically you give us a value between 0 and 255, and from there you go ahead and deduce down and go, oh, color 19 is some kind of red shade, and color 22 is some kind of blue. And so that information is stored elsewhere in a palette, and you would just go ahead and just basically spit out which color goes where. And so it would take 64,000 bytes of storage for this, because 320 times 200 times 1 pixel, or one byte per pixel, gets me to 64,000 bytes of storage. And so coming back, so multiplication, this for me, this is back in 1994, 1995, the IEE standard for floating point arithmetic and multiplication and all this extra stuff hasn't been around for very long. And like in some chips back in the day, like the original Nintendo, had no multiplication. You had to do the math yourself using these kind of operations. So like you pretty much had to live in the Wild West days here. So how would I go ahead and say I wanted to set a certain pixel a certain color? Well, how would I figure out exactly which pixel in this memory buffer? And then figuring out what value to set was simple. I just want color 19 or something like that. But figuring out where was challenging. And so here is some memory, or here are 3 different ways you could go about solving this problem. So the naive method would just take and just say 320 times y plus x, because for every y value you have to move over 320 pixels to get to the next line. And so this will get me there. And so video RAM is just an array. It's just a fancy array. And so 320 times y plus x gets me there. And so coming down one more time, coming into what we're discussing about, well, 320 is powers of 2. It's 256 plus 64. So you could go ahead and shift this value over 8 times to multiply by 256. You could shift it over 6 times to multiply it by 64. Add those two together to essentially get me 320y, and then I add x. And so 2-bit shifts and 2 additions are going to be faster than 1 multiplication and 1 addition at the end of the day. And so taking this one step further, and this is, I don't know if this holds as true today as it did back then, that if you took this and you did the more fancier way of doing doing the syntax of this, of turning this into basically a raw pointer address mode, this actually would speed things up even more. Still no guarantee, but I could tell you back in my day, this line of code is what we used for this kind of thing for every pixel along the way. So coming down one more time just to check out what would happen. What does this look like? I disassembled the 3 lines of code here. This is method 1, method 2, method 3. And you can see that they do not represent, all 3 of them are unique to one another. They might share a little bit here and there, but at the end of the day, they are completely different operations. Just because you see 3 lines of code here, and you see, that doesn't mean anything. Like with that human resource machine game, yes, 3 lines of code is faster, quote unquote, than something that's 7 lines of code. But each operation has a number of clock cycles it takes to operate. So this imul takes a ton of clock cycles compared to a shift left operation and any of these other kind of things, and the load effective address, move operations, and all sorts of other things. So you would have to do some experimentation to see exactly which of the three methods, is the one that works the best on your system. So, in the future, maybe multiplication is faster than this. Who the heck knows how, advances in computer technology and whatnot. But for now, experimentation would tell you that probably the third method is still good. 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. It looks like the same number of lines of code, but move, shift, LEA, move. Yeah, there's less adds there's more adds up here than there are down here. So again, coming back to it, I would put my money on methodology number 3 working. All right, a couple more examples to finish things up here. So rotate a double word stored in a register 32 times over to display each of the binary bits. I did allude to this earlier. So the example the book gave, I think they used shifts and all that stuff. But what's cool about this is, if we work this out, let's see, EBX is the input. It's the double word I want to print. And so what's cool about this, I'm teaching you guys about the pushes and the pops and all the things we have to do to maintain, to make sure that all the registers are put back. But what's cool is if I set ECX to 32, and I'm doing this 32 times over, I rotate to the left, I check to see what's, basically what's stored in the AL register, or I'm sorry, the carry bit. If I'm seeing what's in the carry bit, remember, that's what happens when I rotate. I can set a 0 and a 1 and print that out accordingly. But again, what's cool, I don't have to push and pop EBX, because in the process of rotating this thing 32 times, because this is a 32-bit quantity, at the end, it's put back to what it originally was. So I used every bit. I printed out all of the individual bits that make up this 32-bit quantity, but I don't have to add the push and the pop here, because at the end of the day, it hasn't been modified. So this does it show an example? No, no example, but you could see, like, it would print out all the bits. I think 1023 there's a ton of ones in there, because that's, so that, like, let's see, 23 zeros and 9 ones, if I'm going to be a betting man on this, because 1024 is a power of 2, that's 2 to the 10th power. So 1023 is the largest 9-bit number that can be accommodated. So I would bet 23 zeros and 9 ones if I were to print this out. And so the final example here then, isolating a bit string, coming back to my boring days. Say I had to do this with playing cards, with a poker game, with this kind of stuff, condensed down as much as possible. But like in this case, an MS-DOS file. So like if I go to command prompt here, cmd, and I bring this over, and I just do a dir, like, oh, here's all my stuff. Oh, look at that. I have a OneDrive, or whatever, all the stupid stuff I have. But you see, there's a date associated with every file on here. I mean, that would be a duh, right? And there's also a time associated, but we're not dealing with the time. And so our goal, in this case, their goal as the administrators, the architects of DOS, was to come up with the most efficient way. How many bits does it take to figure out the date for a specific file? And they did it in 16 bits. And so they use 5 bits for the day, because we need from days 1 to 31. So 2 to the 5th power, 32, that works out. So month goes 12, so I can actually use 4 bits. I could go from 0 to 15. There's a little overflow for March and all the other months that we have to worry about. And for year, that gets the leftover number. So that's 7 bits. And so 7 bits gets me a value between 0 and 127, and that's why they decided that 1/1/1980 was the day, I believe it's 1980, was the first day that DOS starts counting from, or Windows, or whatever you want to call it these days. And so it's a matter of, how do I unpack this data so that, the data is all jammed in there, basically, if you want, almost encrypted in a way, if you want to think of it that way, because like this case, like, the DH register, the high end of this thing, or the top 7 bits, the most significant 7 bits are part of the year. But then now the month is tied between DH and DL and all sorts of crazy stuff. How am I going to get that information? So what we could do here is, let's see, to get the month, here you can see here, just move a value over. You don't want to limit, you don't want to blow out the original value. And then I shift everything over 5. And so what does that do? It essentially kicks out the day information, because that's 5 bits. And so the month is now on the least significant side. So the first 4 bits now on the least significant side of the DL register are going to hold the month value. And so now that I've shifted over, I can AND it with 1111. And so because it's only 4 bits that I'm trying to test for, so at the end of the day, and so everything else is zeros. If you wanted to feel better about it, you could put a ton of zeros there, but it's assumed that everything else is 0, and the least significant bits are 1, 1, 1, 1. So when you do the AND operation between, in this case, 0, 0, 1, 1 and 1, 1, 1, 1, you get 0, 0, 1, 1, and you get the 3 out of it. So, and then since that's the DL portion, you could say, okay, or in this case, the AL portion, put that 3 into the month. So that's the second most challenging one of the 3. The day is easy. I don't need to do any shifting because the values are already stored in the correct location. I would just have to do an AND with 5 ones because I want to kick off and eliminate everything but what's in those 5 bits. And now whatever value would be in after that AND, that's the day. And so the year, if you're following along here, the year I just have to shift over 9 times. 5 plus 4, and then I have to do an AND with 7 ones because there's 7 bits that I'm trying to accommodate for. And then once I have that, then I got to add 1980 to it. And it's just because why not, right? So the year 2107, watch out, right? That's when we'll have our overflow for this DOS stuff because that's it, right? When we move from December 31st, 2107 to 2108 or whatever it is, that's when things are going to get real. And I hope Windows has figured that solution out between now and then. So this pretty much covers everything I wanted to talk about in this lecture. The bit shiftings, multiplying by 2, quick and easy, quick, it's not even dirty, right? It's quick and easy to multiply things by 2, shift and left, or divide, shift and left, and shift right. So that's pretty much all there is to it. And so it's a different way of thinking. But again, so I've even seen in comments for my videos already here on YouTube of people saying that, yep, don't use mul if you can. Always think, because we're writing code in assembly language for a reason, because we're trying for efficiencies, either in the amount of code or this, we're trying to reduce the amount of code we write, or we're trying to speed up our code, or we're trying to do both. And so if we're trying to work in, basically in the paradigm of what assembly language is all about, our goal is to make multiplication work as fast as possible, and this handles that pretty darn well. So if you have any questions, you know how to get a hold of me, especially my students, swardb@cod.edu. You guys are great at getting a hold of me there. Comment here. I don't always see the comments. I'm not on YouTube every single day of my life, so if it's important, if you need an answer immediately, definitely send me an email, and especially if there's a correction, because this is my first video back after a while here, so I'm not intentionally trying to blurb up anything, but I might just do that. So thanks for sticking around here, and we'll see you in the next video. Have a good day, everybody.